Jen Pinson. So without further ado, Mike, take it away, and folks just type questions into the chat box, and we'll address them in order at the end. Thanks.
Good morning, and thank you for taking the time to come to my presentation today. I see a lot of friends on this list of attendees, and thanks for coming, and thanks as well to some faces I don't know. Bear with me today. I'm feeling a little bit under the weather. My voice isn't as good as it sometimes might be, but it will be okay. So today I'm going to talk to you about fire behavior, fire effects, and fire regime, and what we can learn from them when we use burn severity as a monitoring tool. Specifically, I'm going to focus on research in the New Jersey Pinelands that I conducted while working for the U.S. Forest Service and as a doctoral student at Rutgers University. So wildland fire is a globally important phenomenon, which we all know, in the Australian bush, in the South African Fimbos, and in forests of North America. Fire managers and ecologists are interested in fire behavior primarily for its public safety ramifications and fire effects for their bearing on environment and associated ecological, economic, or health-oriented management objectives. In a number of these systems, and especially Western North America, fire researchers have been increasingly relying on burn severity as a metric for monitoring fire effects. The picture and the map in this slide illustrate a burn severity map for the cabin fire in Southern California that was created using reflectance data collected by a satellite. And Matt Dickinson is in the other picture there. Thanks for joining today, Matt, collecting field data for comparison. We were out on that fire as a part of a fire effects monitoring effort a couple years ago. So burn severity, as described by Key and Benson, is the quantity or scaled index gauging the magnitude of ecological change caused by fire. Essentially, it's the sum of ecological change in an area. Burn severity is most commonly derived from freely available reflectance data collected by USGS satellites, typically those of the Landsat program. The reflectance data in that these satellites collect is segmented in specific bands or ranges of wavelengths, like the visible spectrum or infrared range. Burn severity is typically derived by combining near-infrared reflectance, which is sensitive to changes in live and dead foliage reflectance, and mid-infrared reflectances, which is sensitive to increases in char and altered soil properties. The resulting data is often validated then using a field method of estimating burn severity. Numerous ecological effects have been identified to correlate with burn severity or altered reflectance. In the Pacific Northwest, researchers have identified patterns in basal area reduction that correspond with burn severity. In the Sierra Nevada, an analysis of historic reflectance data has revealed that burn severity has been increasing in recent decades. These researchers used archived Landsat data, which again is freely available from 1984 on, thus presenting a unique opportunity to go back in time, so to speak, and analyze previous fire events. So, okay. So this brought a couple questions to mind that I thought we could answer in the New Jersey Pinelands. Burn severity research hasn't really been conducted, or burn severity techniques haven't been used that widely in the eastern United States, while they have been used more commonly in the western United States. And we were doing a number of projects with burn fire effects and fuel consumption, as well as fire behavior, where I thought we could integrate these approaches to learn a little bit more. So this work really focuses around three separate studies, I guess you could say, and they answer three questions, or are aimed at three questions. So the first one is burn severity related to fire behavior? So that's important because burn severity is really just focusing on or is really just a measurement of light or observed change, but it's not actually a physical measurement of something like fire behavior that we're clearly interested in. Second question is, can burn severity explain fire effects? How well are those changes in reflectance linked to aspects of the forest that we're interested in managing, such as fuel consumption or tree mortality in the event of overstock stands or stands that we're trying to thin, perhaps for resilience against southern pine beetle? The third question is, what can be learned about the fire regime of the pinelands from burn severity data? And this uses the archive Landsat data to look at fire size, fire type, and seasonality, and how they may play into patterns in burn severity. So, as you probably know by now, all this work focused in the New Jersey Pinelands. And the New Jersey Pinelands is one of the few places in the Northeast where a little bit of burn severity research has already taken place. A couple of years ago, we demonstrated the potential for burn severity for using remotely sensed data to monitor burn severity at a series of prescribed fires and a wildfire in the Pinelands at Penn State Forest. And this showed that there was a strong agreement between reflectance-based burn severity and field-based burn severity. So the first question is burn severity correlated with fire behavior? Measuring fire behavior is pretty difficult. There aren't really any good off-the-shelf tools for doing this, and it can be prohibitively time-consuming and expensive to do this across any broad space. One of our colleagues, Eric Mueller, he's in that picture right there, he developed this neat little piece of custom fire tracking equipment which measures temperature of a thermocouple, seen right here. That's the end of the thermocouple, as a surrogate for fire intensity. This little device is placed with this part underground and the thermocouple sticking up, and it can be burned over during the fire. These instruments can be rapidly deployed across burn units to collect spatially relevant fire behavior data. That map on the left is just a image of how they could be deployed or how they actually were deployed. So we actually used 2 field sites in New Jersey and a 3rd field site in Florida to test this approach. The one at Tall Timbers in Florida was a longleaf pine stand. And this map on the left shows fire intensity, or essentially it's peak temperature measured at those thermocouples, which we're using as a surrogate for fire intensity. This part of the study was conducted at the Franklin Parker Preserve, and we went back after the fire and measured burn severity using a field method at each of the fire tracker locations, which are the little black dots on the map. As you can see from the regression on the right there, there's a pretty strong agreement between burn severity and that peak fire temperature. We could also derive residence time from that data. And on the left now you see a residence time map in minutes. And that relationship with burn severity was not as strong. So I went ahead and I made a little model to try to figure out how these two things related to burn severity, how this peak temperature and residence time led to specific burn severities. And what I found is that the residence time and the interaction between residence time and peak temperature really had little to do or provide little additional information about the resulting burn severity. And so what we can take home from this is that burn severity, at least in the studies that we conducted here, was more closely related to surface intensity than residence time, and that fire behavior only explains part of the burn severity observed. So our regression only had a 0.6 R squared, which is pretty good. I considering the approach, but it also suggests that there's something else out there that's driving burn severity. So the next part of the study was looking at fire effects, and now that we have a link between burn severity and fire behavior, there's a mechanism there. And so how does burn severity predict fire effects? So the first thing I'd like to talk about is the consumption of surface fuels, and that's important to fire management because surface fuels are considered to be proportionate to the risk associated with a piece of ground or how manageable it would be in a wildfire event. So we went out to 30 different burn units. Some of them were wildfire burn units and some of them were prescribed fire burn units. In the wildfire burn units, well, what we did at all those sites is collect fuels before and after the fires and computed fuel consumption for those areas, and then went back and used both the satellite and the field methods to also estimate burn severity at those locations. And so for the wildfire site, because we didn't know where they were going to happen before they happened, we used the opposite. We picked sites that were close to a plowed control line through the basically bisecting what was originally the stand, and used the unburned area as the pre-fire condition and the adjacent burned area as the post-fire condition. So what we found is that fuel consumption went up with definitely increased with burn severity. You can see in the top part of this figure here, this is showing relative consumption or the percent consumption as it varies with burn severity. At the bottom here, this is absolute consumption, so the actual tonnage per acre, or tonnage per hectare actually. And what's interesting is that the field method, you can see, did a better job of predicting consumption than the remote sensing method. But what it also shows is that substantially more fuel is consumed. So this is surface fuel, so shrubs and litter on the forest floor. Substantially more is consumed when you have a moderate severity fire. Another category would be high severity, and we didn't have any sites that fell into that range, unfortunately. But you can imagine that would have even more consumption. So the result of this showed an increased consumption with higher severity, basically, and that the composite burn index, or the field method, did a better job of predicting consumption than the remote sensing method did. So another fire effect that I was interested in was tree mortality. Does that covary with burn severity? So at some of the same sites and some additional sites, we measured mortality rates of pitch pines, and these were in almost purely pitch pine stands. And what we found is that that mortality varied with burn severity and by tree size. And so this figure on the right here, you can see curves that show the probability of mortality, that's on the y-axis, varying with burn severity levels on your x-axis. And so basically a 5-centimeter DBH tree is going to die a lot sooner than a bigger tree, which is intuitive, and that makes sense because it's going to take more heat to get through a larger tree's bark. What's interesting about that is that that the remotely sensed burn severity index actually produced better estimates than the field method, and so that's kind of an interesting juxtaposition there, that the field method works better for predicting fuel consumption, but the remote sensing method works better for predicting tree mortality. And an explanation for that that's most plausible is the satellite is looking down from above at the forest, and so most of what it's seeing is going to be forest canopy as opposed to what's beneath it. And so the change that I believe it's most receptive to is going to be that of the canopy versus the forest floor. All right. So the next segment here is looking at burn severity and fire regime. And I had some questions about how does seasonality affect burn severity? How does fire type affect burn severity? How does fire size affect it? And are fires changing on this landscape? And so for this portion, I went back and looked at Landsat data. And this slide and here is just showing that we've got a lot of fire perimeter data over the past 50 years, or actually going back to the 1930s. Inga actually mapped quite a lot of these perimeters for her dissertation, and we can learn a lot about the fire occurrences here, how often a large fire occurs, how many acres a year burn. But what we miss is, or we can learn about the fire size and how much area was burned through time, how frequent fires occurred. But what we miss is what was happening inside those perimeters. And this is a fire report from the fire in 1953, the Paradise Fire. And this report that was written by Silas Little actually details a lot of variation that happened within the burn unit in an area that didn't burn quite as harshly as some other parts, and how they chased the other parts around throughout the day. And those are the types of things that really get lost in just mapping perimeters. And that's something that burn severity can kind of fill in the gaps for. And so I went and I used perimeters of fires from 2006 to 2015 to extract burn severity of all those fires during that period out of Landsat-derived coverages. And so what it looks like when you do that is you get a map that looks somewhat like this on the left. This is the Warren Grove fire, and this is a histogram of the pixel values. And so the brighter the pixel, the more severe that pixel was. And so this histogram shows the distribution of those pixels for that fire, which was the largest fire in recent history in New Jersey. This is the Atsion Fire, and you can see it has a much flatter distribution. This fire happened in the same year, a bit west of there. And then this is a typical prescribed burn using the traditional plow line. That's what all those striations are, going north-south. Those east-west striations are actually missing data due to an issue with the sensor. But you can see that there's a lot of variation in how those in burn severity in those different fire types. And so this is just a description of the data, essentially. This figure shows how many fires were observed in each year, how many wildfires in orange and how many prescribed fires in blue. Overall, there were 446 fires included in this portion of the study that occurred in that time. The majority of those, I want to say probably 4/5 of those were prescribed fires, and the rest were wildfires. We didn't include very small wildfires, which make up the bulk of the fires in the landscape here. New Jersey continues to have approximately 1,000 wildfires per year, but the majority of those are very small, so small that really they don't match up with the pixel size of Landsat data. And so one of the questions was how might burn severity be changing through time? In that study of the Sierra Nevada, they showed that burn severity was actually increasing over the past 30 years or so. And my study only went back to 2006. It's just a snapshot of the most recent 10 years. I'd like to go back farther, but I haven't had the time yet. And what this figure shows on the left is we have the year on the x-axis and burn severity on the y-axis. And what it really says to me is that we probably should go back farther. That severity of prescribed fires isn't really changing or is actually decreasing, and the severity of wildfires might slightly be increasing. I'm sorry, vice versa. Essentially, though, the data is pretty scattered, and probably going back farther would give a better picture of the trend. One interesting thing, though, about this small 10-year snapshot is that there was a correlation between the severity of wildfire in a year and prescribed fire in a year, such that years with more severe wildfires also had more severe prescribed fires, and that's illustrated in the figure on the right there. And that might just have to do with variation in weather events from year to year. The next slide here shows a bit about how fire size is important. I've separated out wildfire and prescribed fire. So on the left here, we have a figure that shows the log fire size on our x-axis and burn severity on our y-axis. And the yellow dots show the maximum severity of a fire, while the blue dots show the average severity. And both average and maximum severity increase with wildfire size. But interestingly, if you move over to the right here, the relationship is pretty poor for prescribed fire. And there might be a seasonal component there as well, as prescribed fire typically happens in the dormant season, mostly in March and February, whereas wildfires happen throughout the year. Another way I divided up the data was to compare wildfires and prescribed fire severity. And this is just for March, because that's the primary time of year that we prescribe burn. So these are March wildfires and March prescribed fires over that 10-year period. And what this figure shows is in orange, we see that the prescribed fire severity, the fraction of area burned, that's our y-axis, is skewed towards a low severity. While with wildfires, the distribution extends much farther into the range of severity possible. And so we have a lot more of a wide distribution, and subsequently there's probably greater effects from wildfires. Now, one explanation for that also is that prescribed fires are conducted under specific prescriptions, whether prescribed fires. Wildfires may be occurring on days that are out of prescriptions that are more hazardous, and that could be that's one explanation of why the severity of wildfires is different. So, with prescribed fires, we're not trying to burn any homes down or anything like that. We're trying to keep them relatively safe, and so there's a window of prescription to facilitate that. And so that's my guess as to why these two are so different at this time of year. So that brings us to seasonality of fire. And what I've done in this figure is I classified severity into no effect, which doesn't mean it didn't burn. It just means it's an extremely low severity. There's low severity, moderate severity, and high severity shown in green, yellow, orange, and red. And what this shows is that we have January, we have the month of the year on our x-axis here, and we have the fraction of area burned in that month on the y-axis. And what this shows is that during January and February, it looks like we lost the J and the F for those months, but in January and February, actually, we could go from November, we look at the end of the year, November, December, January, February, that's most of the prescribed burn window available right now. The severity observed is low to none, essentially. March represents the end of our prescribed burn window here, and at that time you just start to get a little bit of moderate and high severity activity. And then as the year progresses, the severity proportion of moderate and high severity pixels increases substantially through August, and then once the fall rolls around, it tapers off again. And so that's important again, because there's also well, because we only burn actually from October through March right now with prescribed burns, mostly in March, and that's the dormant season. And then this time of the year where you see a greater effect is actually the growing season. And so that's just an interesting factor there. So I was interested in applying these severity trends to some of the effects that I had observed in the second study with fuel consumption and tree severity. And so if we know the proportion of area that has these different types of burn severity, we can then multiply through these different relationships with consumption and tree mortality to see how these rates might actually differ in different times of the year or with different types of fire. So I went ahead and I multiplied through the consumption rates that I had observed with the actual observed proportions of area burned with different severities and estimated the surface fuel consumption by month. And so what we have on the y-axis this time is percentages of the total available surface fuels that would have been consumed for these different months of the year. And so what you can see is that definitely during the growing season, there's a bit of an increase up to close to 75% of those surface fuels being consumed, whereas during the dormant season, we have about 48 to 55% of fuels consumed, with it starting to creep up a little bit more in March there. Also, here's a slide about tree mortality rates, and I was comparing prescribed burn and wildfire proportions of pixels in March to see how rates of pitch pine mortality might vary between prescribed fires and wildfires in that time of year. And so on that figure on the right, we can just be reminded of how those severity trends differ. And if you multiply it through, you'll see that prescribed fire in the brown bars kills far fewer pitch pines than a wildfire at that time of year might. And so we're only killing less than 20% of our 5-centimeter trees, which is a pretty small tree, and of our 15-centimeter trees, which isn't even that big, we're really killing less than 5% of them. And that's important because our stands are overstocked, and it's expensive to harvest trees to thin the forest, but fire at this time of year might not be the most practical way of doing that, or at least not even the prescriptions that we have right now. And so I'd like to extend this to the region more by using FIA data and actually looking at estimated stocking of different size classes of trees and actually looking at how much the forest is growing versus how much prescribed fire is actually reducing it, and how if we change our methods or our approach, how would it be possible to thin more of the forest? So I'd just like to conclude those different studies. Again, the first question was, is burn severity related to fire behavior? And we found yes, it is, and that surface intensity or the at least our thermocouple measurements predicted severity better than residence time did. Actually, this should have been our third question, but what can be learned about fire regime in the Pinelands from burn severity data, and that is that fire size, at least for wildfires, is important in determining what severity will be present, and as is fire type, seasonality, and then the decadal trends were a little bit less clear. Then also can burn severity predict fire effects in pitch pine barrens? And that seems to be yes. We found a strong relationship between burn severity and mortality rates of pitch pine, as well as consumption rates of surface fuels. And then lastly, applying fire effects trends with burn severity patterns that we observe across this landscape can help us monitor not just burn severity, but some of the effects that we're trying to reach or trying to avoid, and help us figure out how to better plan our management on this landscape. So with that, I'd just like to thank a couple of people here. A lot of this work was supported through other joint fire sciences projects, as well as the New Jersey Forest Fire Service, Eric Mueller, Chris Thomas, Rory Haddon over at the University of Edinburgh have all been very helpful in these studies, as has Ken Clark and Nick Skoronsky, my colleagues here at the U.S. Forest Service, and Tim McWilliams, our most recent addition to the team, and Inga LaPuma, who really did an excellent job of putting together a lot of this fire history research during her dissertation. And it's exciting to build on her work and also that of Nick's that he conducted before me. And so with that, I'd like to open up the floor to any questions.
Great, Mike. Thank you so much for that webinar. So this is really great. We had a couple of questions. Now we have more presentations more questions that are coming in. So Bob Cremens asked at the picture with the thermocouple. He said, "Where is the thermocouple placed for fire tracker devices?"
Hey, Bob. So the thermocouple was situated about 10 centimeters above the surface of the litter. So the bottom of the tracker that had the guts in it was buried just under the soil surface, and we minimized our disturbance as much as possible. And then that thermocouple stuck up, like I said, about 10 centimeters above the litter layer. Okay,
great. Bob had another question on I think on the monthly burn severity graph. He said, with the burn severity levels, high, moderate, et cetera, developed for western fires, are these levels relevant for your ecosystem?
Yeah. So that's an excellent question. And yes, they were developed for western fires. Those are the so I used the strictly went from the protocol from Key and Benson, 2006 FireMon. It's available online, and there's a field sheet and a whole description of how to do the field method. And so those levels of severity were defined originally with the Western United States in mind, and they may not be as relevant here it really depends on what your question is. But as far as the class, coming up with some classes to show that there's a difference, I think they're somewhat useful here. But there hasn't really been much work in redefining.
All right, thank you. We had a question from Faith Berry. She says, will a paper be available?
So a lot of this work, the fire trackers are pretty new, and some of the synthesis is a little bit new, but a lot of this work is in my dissertation, which if you email me, I'll send you the PDF. It's supposed to be online, and I haven't been able to find it. I'm not sure when it'll become available online. I guess I could post it on ResearchGate. But if anybody is interested in, it's all written up in my dissertation document. I could pass that along. And then, of course, I am writing this up for publication right now, actually.
Sounds great. I just pasted your email address into the chat box, so everybody can email Mike to get a copy of his dissertation. And everybody, feel free to type more questions into the chat box. Bob's got another one already. But before that, Neil Gifford has a question. He says, great presentation, Mike. And then his question is, with all your tree mortality data based on dormant season fire, we have observed larger fires being more vulnerable to growing season fire than dormant fire.
Neil, that's a good question. Most of the fire, but not all the fire, was dormant season. There were actually all four of the wildfires were, I believe, no, actually two of the wildfires were growing season fires. One was in the end of April when things started growing, and then another one was in July. But yeah, that is one shortcoming of this study, is that we didn't have the opportunity to measure this effect in every season of the year, or every month of the year for that matter. And I forgot to point out in that figure, let me see if I can find it here. Here in the figure, if you can see where the dotted line is, these solid lines turn into dotted lines. That is where we actually, our data cuts off. So everything that's dotted there is estimated based on the relationships that we observed for lower severity fires, but we actually didn't have a ton of extremely high severity fire available during our study. And there also there were far more smaller trees, or trees that were less than 30 centimeters in diameter than greater than that. And so it would be beneficial to extend it'd always be better to collect more field data, right? And measure some larger trees and over a broader range of seasonality.
Great, thanks. Bob Kremen says a follow-up question about the thermocouples. He says, okay, the reason I asked the question about the thermocouples is that a diffusion-limited fire will always be about 1100 degrees Celsius, so the temperature might be related to the residence time and the response time of the thermocouple.
The temperature might be related to the residence time, response time. Yes. So I actually didn't include it, Bob, but we did some laboratory studies with the thermocouple, comparing it to the finest wire thermocouple that we could measure. And that's why I said before that it's kind of it's related to fire intensity, or it's really what that's measuring is the temperature of the thermocouple, which has some thermal inertia, and so it doesn't respond as fast as the change in temperature of the air does. But while it doesn't respond as fast or hit the same high peaks as the actual air in that fire environment is reaching, it is closely related. It's proportional to that, the actual temperature. One of the troubles is that these fine wire thermocouples, if you haven't seen them before, I know you have, Bob. I mean, they're like spider web thin, and just getting one of them to the field without breaking it is next to impossible. I think we actually played with that at Warren Grove a couple years ago. But the point is that there's a strong relationship there, even with an instrument that's kind of a blunt tool still, and so that's pretty encouraging, and basically shows that there is a relationship, and I'm not sure if it actually matters how absolute that is at this point.
Great, thanks. Bob says that that's the answer he was looking for. So, all right, we can give folks more time to type some more questions into the chat box. I'm sure that people have questions for you. I wonder if you can jump the slide back, Mike, to the your questions and answers slide. It's like almost like second from the end, maybe.
Yeah. There we go.
Yeah. All right. Yeah, we'll give folks another moment. Maybe looking at the conclusions might jog a few questions. I guess while people are typing, I have another question for you. It's if you were to continue expanding your research, it seems like one question leads to another. What do you see as the next most important question, kind of building off of your research that you would want to dive into?
The next most important question. Well, I would say actually going back and filling in the gaps back to 1984 from the archived reflectance data. And so I'm really interested in kind of knowing how, so before 1984, we didn't really have the ability to do anything better than, drawing fire perimeters and giving them a date and knowing, whether a wildfire or prescribed fire happened in that spot on that day. But to be able to go back now and kind of make a benchmark of where we're at, where we were at in 1984. That's when the satellite that collects this data for the first one was launched. We can start to look at how fire. If we have that data, we can look at how fires changed over time. We can pull in other data feeds like weather data from those days that those fires occurred on, and start looking at how there's thousands of fires that have occurred since 1984, and even if we don't know exactly what where the fire was at what exact time, having the distributions of those different weather parameters during those days and those fires can be all integrated into a meta-analysis to really look at how fire behavior and weather interacts and how these things are changing, and make some estimations of how things might change in the future, or how we can use that information to further tweak our management approaches.
Yeah. You have a positive comment. Quincy Jones says the thermocouple slides and video was very interesting, and I enjoyed seeing the work. And building off what you were just saying, John Bonnell has a question. He says, has anyone ever assessed the landscape using remote sensing after a wildfire to see if the severity was lower in the areas that had been prescribed burned in the past versus areas that had no history or recent history of prescribed burning?
Yeah, so that's another good question. I haven't gotten there. I started looking at it, and there there's just a lot of directions to go, and I was trying to finish, but that wasn't the primary focus of my dissertation, and it kind of came a point where I just had to stop asking new questions and finish the ones that I'd come up with first. But that's another avenue that I would like to pursue. And that's an interesting question, or an astute question, and one that has been looked at in California. And there's a study, a couple studies that show decreased burn severity in previous fire scars. And so, yes, there's likely an effect there. So that's something that I'd like to look at more. Yep, and Bob just seconded that response.
Yeah. Bob says there have been papers about lower fire severity in areas that have had wildfires in recent times from the western fires. So, yeah, great questions, great comments. We definitely have time for more questions, so feel free, folks, to type some in. Another angle that, just to kind of expand on that, another angle that we were hoping to look at, Nick and I was looking at how forest structure before a fire influenced the burn severity that occurred there, and so we're kind of working on a study with that right now. It's kind of his, he's the lead on that, but just seeing how pre-fire structure and density of vegetation might influence the resultant effects or on severity. Yeah, definitely. Forest structure is certainly a challenge in a lot of the North Atlantic landscape. So that would be a really important question to look at. So I guess going back, and again, folks, feel free to type more questions into the chat box. So you had a slide that talked about kind of how the field CVI method worked or seemed to be more accurate than the remote sensing method. But so how do you see kind of tying everything together? How do you see those two tools working together? Where do you think it might make sense to use remote sensing versus field method versus combined method, given the ownership landscape in New Jersey and across our region actually? Where do you think one tool versus the other might be more useful, or a combination of them?
That's a great question. For a landscape scale approach, remote sensing is hands down the way to go. Even though the field method is quick, a day or two in the office, if you know what you're doing, you can estimate the burn severity using the remote sensing method very, very quickly. And you could still go out and do some validation plots in another day or so, a couple days, and have a great data set. But the one biggest limitation I see to that is that you need some somewhat expensive remote sensing software. ArcGIS will get you there, and you just need the skills to do it, which aren't prohibitive to learn. Anybody could pick them up with banging your head against the wall for a little while. But the other thing about the remote sensing method is that it's also repeatable. So the field method is somewhat repeatable, but there could be bias by different observers, whereas when you're using that remote sensing method, it is what it is. I thought it was interesting that tree mortality actually was more correlated with the remote sensing approach than the field approach. But the field approach could be beneficial if you're a practicing forester who doesn't have ArcGIS, or the skills to do the remote sensing approach, or maybe you're managing an area that's smaller than the pixel size of Landsat data. So that's a 30 by 30 meter pixel. Maybe you're just trying to measure fire effects on a small property for some farmer or landowner, and a few plots in a day could give you the answer that you need. That's where I see an advantage of the composite burn index method, that field method.
Got it. Thank you. Let's skip over another.
All you really need for the CVI approach is a piece of paper and some time to go out and record data.
You had a little bit of that working on your dissertation.
Yeah, and actually, just one more comment on that. We actually went over that method at the Albany Pine Bush earlier this year at the capstone workshop, and one of the questions before we started doing it was, everybody's going to see the forest differently, and so what good is this going to be? And so we split up into groups and had different people go out and try this approach in groups on some of the same spots. We rotated around these different plots. And what we found is that everybody had pretty similar results actually. And because you're looking at a number of different factors and integrating a whole bunch of them together, if one person sees one thing a little bit differently, it kind of all works out in the end. When you integrate all the factors together, that you get a pretty similar result.
Yeah, and I think we put your presentation on the NAFC website from that field workshop. Inga can correct me if we didn't, but I think we have that available. So let's see. I think we have another question or comment that came in. John Bonnell says, great talk, Mike, and thanks, Bob. I would assume that wildfire is less severe in areas previously burned by wildfire. However, it seems as though we should learn whether prescribed burning reduces wildfire severity. Not knowing that makes me wonder why we are doing prescribed burn.
Yeah, well, I mean, yeah, I mean, we should study that. I would say to that as somebody who's managed some fires both here in New Jersey, and I've worked on some fires in prescribed burns in New York and Florida, as well as on some wildfires out west. I can say that areas that have been treated definitely respond differently, and or typically easier to manage. And there have been certainly wildfires in the Pinelands that I've worked on where you can observe a change in fire behavior, such that it becomes much more manageable where there was a recent prescribed burn. So I think what maybe a good approach there would be looking at the sort of the residence time of the effect of a burn, looking at different severities. So, if you do a cool prescribed burn or a hot prescribed burn, or you have a cool wildfire or a hot wildfire, how long does that effect last for? And to what conditions will that really stand up to? So it's kind of I think of it as sort of a spectrum. Any treatment is going to do something. Just sort of knowing how far it will get you.
Yeah, and Inga is adding a comment on that. She says, depends on the time since fire. If a shorter rotation, less than 4 years, then it definitely helps. And Ken Clark also added, Mike, great talk and thanks for presenting. He said, this study has come along very nicely. Linking the metadata may provide even better predictive power. So let's see, we're getting close to the top of the hour. We have just a few more minutes. We could probably answer another question or two if folks want to type something in.
So,
this is great. Go ahead.
I guess just one more follow-up about prescribed burning is that, even a cool prescribed burn is going to reduce your fuel loading and the continuity of fuel. If we go back to if I can find it. Here, we can go back to this figure. Even the cool prescribed burn, we can see right here, produced, according to the CBI data, 47% of the surface fuel, and 63% of or 63% according to the remote sensing data, and so I guess. That does impact sort of the ignitability of an area. So, in my opinion, maybe around homes or something like that, that's a useful tactic where you might not want to risk doing a more severe fire that's going to be more volatile, and maybe your concern in that sort of area is just preventing ignitions from happening, which I think could be done. With some less aggressive fire. And so I think there's different places for different sorts of fire depending on the goals or the risks associated with them. It's pretty complex landscape and managing fire and integrating those different sort of factors is kind of a complex question as well.
Yeah, Bob Cravens just added, I'm sure the interval between fire of any type and the severity of subsequent fires is highly correlated. It also depends on the growth rates, productivity related to soil fertility and rain and sun, and decay rates as to the fuel loading or fuel availability for the next fire event. So a lot of factors are in there. Well, I think we're just about. Okay, good. Yeah. We're just about at the top of the hour. I think we probably better cut off questions at this point. But again, Mike, thank you so much for presenting your research. You covered a lot of topics and a lot of really good questions. And thanks for everybody who participated in the webinar today. You also had very good questions. And this webinar will be archived on the North Atlantic Fire Science Exchange website. It's our last webinar for 2017, and we're going to plan a good series for you in 2018. And we look forward to seeing you all, hopefully, at Igniting Exchange in Portland, Maine, our partners meeting with the Northeastern Forest Fire Protection Compact at the end of January. So thanks, Mike, and thanks, everybody.
Yeah, thanks, everyone, for tuning in. Have a good afternoon.
Yeah, you too. Thanks. Take care.